Good morning, bro.
Morning.
How is Malaysia?
All right. Good.
I was sleeping. I have to wake up.
For a while.
I'm in my room.
Yeah.
No, bro.
Congratulations.
Thank you.
Hello, friends. I welcome you all to TechMite. I hope you all are doing well. Today's video is about robotics. Almost all of you have heard this term, and most of you might have studied about it. Let's do a quick revision together. Starting with the definition. Robotics is the intersection of science, engineering, and technology that produces machines, called robots, that substitute for or replicate human actions. A little bit more common term than robotics is robot. A robot is the product of the robotics field, where programmable machines are built that can assist humans or mimic human actions. Robots were originally built to handle monotonous tasks like building cars on an assembly line, but have since expanded well beyond their initial uses to perform tasks like fighting fires, cleaning homes, and assisting with incredibly intricate surgeries. As technology progresses, so too does the scope of what is considered robotics. In 2005, 90% of all robots could be found assembling cars in automotive factories. These robots consist mainly of mechanical arms, tasked with welding or screwing on certain parts of a car. Today, we're seeing an evolved and expanded definition of robotics that includes the development, creation, and use of bots that explore Earth's harshest conditions. Robots that assist law enforcement, and even robots that assist in almost every facet of healthcare. While the overall world of robotics is expanding, a robot has some consistent characteristics. 1. All robots consist of some sort of mechanical construction. The mechanical aspect of a robot helps it complete tasks in the environment for which it's designed. 2. Robots need electrical components that control and power the machinery. Essentially, an electric current, a battery, for example, is needed to power a large majority of robots. 3. Robots contain at least some level of computer programming. Without a set of code telling it what to do, a robot would just be another machinery. Inserting a program into a robot gives it the ability to know when and how to carry out a task. Let's talk about the uses of robots. Robots are largely used to perform various tasks and to make human life easy. They are widely used in manufacturing, assembly and packing, transport, Earth and space exploration, surgery, weaponry, laboratory research, and mass production of consumer and industrial goods. We will discuss their uses in detail in another video. Till then, stay connected. That's all for today, guys. If you liked the video or learned something, then please support me by liking it, sharing it, commenting on it, and subscribing to TechMite. If you want to see helpful and informative posts on technology, then do follow me on Instagram. I will put the link in the description. Thanks.
Ladies and gentlemen, we will start at 10 a.m. Waiting for other participants to join. Please be patient.
Check out this product. It's actually making profit a week and it's
Welcome you all to TechMite. I hope you all are doing well. In previous video, I told you about robotics in detail. In today's video, I will tell you about different types of robots. Hello friends. Hello friends. I welcome you all to TechMite. I hope you all are doing well. In previous video, I told you about robotics in detail. In today's video, I will tell you about different types of robots. But before that, let us quickly revise that what are robotics and what are robots. Robotics is the intersection of science, engineering, and technology that produces machines, called robots, that substitute for or replicate human actions. A robot is the product of the robotics field, where programmable machines are built that can assist humans or mimic human actions. Coming back to the topic, mechanical bots come in all shapes and sizes to efficiently carry out the task for which they are designed. All robots vary in design, functionality, and degree of autonomy. From the 0.2 millimeter long RoboBee to the 200 meter long robotic shipping vessel VineSkip, robots are emerging to carry out tasks that humans simply can't. Generally, there are 5 types of robots. 1. Pre-programmed robots. 2. Humanoid robots. 3. Autonomous robots. 4. Teleoperated robots. 5. Augmenting robots. Let's discuss these types in detail. Pre-programmed robots. Pre-programmed robots operate in a controlled environment where they do simple, monotonous tasks. An example of a pre-programmed robot would be a mechanical arm on an automotive assembly line. The arm serves one function, to weld a door on, to insert a certain part into the engine, etc., and its job is to perform that task longer, faster, and more efficiently than a human. Humanoid robots. Humanoid robots are robots that look like and or mimic human behavior. These robots usually perform human-like activities, like running, jumping, and carrying objects, and are sometimes designed to look like us, even having human faces and expressions. 2 of the most prominent examples of humanoid robots are Hanson Robotics' Sophia and Boston Dynamics' Atlas. Autonomous robots. Autonomous robots operate independently of human operators. These robots are usually designed to carry out tasks in open environments that do not require human supervision. They are quite unique because they use sensors to perceive the world around them, and then employ decision-making structures, usually a computer, to take the optimal next step based on their data and mission. An example of an autonomous robot would be the Roomba vacuum cleaner, which uses sensors to roam freely throughout a home. Teleoperated robots. Teleoperated robots are semi-autonomous bots that use a wireless network to enable human control from a safe distance. These robots usually work in extreme geographical conditions, weather circumstances, etc. Examples of teleoperated robots are the human-controlled submarines used to fix underwater pipe leaks during the oil spill, or drones used to detect landmines on a battlefield. Augmenting robots. Augmenting robots either enhance current human capabilities or replace the capabilities a human may have lost. The field of robotics for human augmentation is a field where science fiction could become reality very soon. With bots that have the ability to redefine the definition of humanity by making humans faster and stronger. Some examples of current augmenting robots are robotic prosthetic limbs or exoskeletons used to lift hefty weights. That's all for today, guys. Don't forget to subscribe, like, comment, and share. Thanks.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And a very good morning. Can you hear me?
Yes.
Okay. Thank you very much. So today is second international CMED webinar. Okay, so we are live to Indonesia, Nigeria, and overseas country. Okay, so our topic today will be on the robotics and applications. As you all know in the introductions, robotic application being used in increasing variety of industry, as mentioned in our intro video just now. So we have 4 speakers today for our international CMED webinar. Okay, the first speaker is Dr. Saiful. Okay, so Dr. Saiful will give a talk on the robotics application in agricultural system. Let me introduce to you Dr. Saiful. Brief background: Dr. Saiful is the youngest staff of Department of Control and Mechatronics Engineering. Graduate bachelor degree in mechatronics from UTM, and after that fast track PhD. Recently graduate in robotics, PhD in robotics. So Dr. Saiful currently is a senior lecturer at the Department of Control and Mechatronics Engineering. So without any further ado, I will invite Dr. Saiful to present his research work, robotics and application in the agricultural industry. Silakan.
Right. So thank you to Prof. FUA'AD for inviting me to giving a sharing session for today. So can you hear my voice?
Yep.
All right. So today I will share to you some of the experience that I have in robotic application in agricultural system. All right. So basically, this is I think.
Yeah. Okay.
All right. So this is the table of contents, which is the layout which reflect to the presentation today. Right. So for the first section, I will introduce some of the related, we call it introductions in agricultural operations. And the second part is on the projects that has been conducted. So I will explain some of the applications that has been implemented in the project. And then the third one is I will be also sharing a research attachment that I've had gone right to Kyoto University. And lastly, the conclusions of my presentations. All right, so a brief about my biodata. All right, so basically I graduated from Bachelor of Engineering Electrical Mechatronics from UTM on 2015. And then on 2019, I graduated a Doctor of Philosophy in Electrical Engineering, UTM. And for my PhD, I've been supervised by Associate Professor Dr. Shikri, which is one of the speakers in today's session. Right. So in terms of my work experience, so on the 1st October 2018, I've become the graduate research assistant at UTM. And then on the 1st March on 2019, I have becoming a research engineer at Nasri Mewah Enterprise. And then I've started my career as a senior lecturer on 15 September 2019 as a senior lecturer in Control and Mechatronics Department, FKE UTM. So I am also a member of a research group called ECRG, Advanced Control Research Group. And I am also an associate member of Center of Artificial Intelligence and Robotics, Cairo, UTM. Right. So let's proceed with the sharing session. Okay. So first, I wanted to introduce to you what is actually a precision agriculture. So in agriculture, we have a term called precision agriculture, which is actually a modern farming management, right, concept, which is by using the digital techniques to monitor and also to optimize the agricultural operations. So as we all know, agricultural area is a very wide areas, right? So for example, if we wanted to treat the plants or if we wanted to supply the water to the plant, if we supply the water the same throughout the field, throughout the wide field, it will waste some resources. Okay, so what a precision agriculture reflect is that we just give sufficient treatment at the right place and at the right time. So it means that we just treat the plants or we just give the nutrients, the water to the plants only to the area or to the plants which is only needed the treatment, right? So why we actually introduce a precision agriculture is because it is used to provide low input, high efficiency, and sustainable agricultural productions. So in order for us to fulfill the precision agriculture, what we need to have is modern technology. So modern technology such as a control system, digitalization such as IoT, cloud computing, and also some advanced technologies such as satellite imaging, and also with the help of drones, robotics, and also automation system, which actually can help farmers to achieve a precision agriculture to minimize the resources from their operation. Right, so the main objective of precision agriculture is to improve the productivity of the farmers and also to give a very good impact to the society, right? So we as a university, what we focus here is that we wanted to develop the skills of our students so that they will be able to develop a system or a technology that can help the farmers to achieve the objective of precision agriculture. Right. So in terms of agricultural robot implementation, there are several implementation. So right nowadays, there are lots of implementation that can have been implemented in agriculture, such as in inspections, where the robot, it is used to inspect the maturity of the fruits, where it is also used to inspect we call it the disease level of the plants and so on. Right, and then robotics also has been implemented in spraying operation, where it is being used to spray the pesticides, okay, where it is used to give the nutrients to the plants, spray some plant enhancer and so on, right? So where we use robots to ensure that the plant can be treated at the right place and at the right time. Right, and the last one is the harvesting, which is the most widely implementations of robotics in agriculture, where they are using robotics to harvest the fruits, harvest the vegetables, and so on. Right, why we apply the robots in agriculture? The first one is to improve the quality of fresh produce. So robotics, they doesn't have any emotions like human. So for example, if human, they have some problem with their boss and so on, they will not doing their work sincerely, or maybe they will affect the quality of the fresh produce, right? But the robot, they just do what they are instructed to do automatically without any emotions, right? So that is why it is actually be able to improve the quality of fresh produce, right? So the second one is it reduce the production cost, because when we have a very wide agricultural areas, so we need to have a lot of workers. So for robots, if we have a wide area, only 2 to 3 robots can also can already cover all of the areas. All right, the third one is to minimize the drudgery of manual labor. So the drudgery term here, it is actually reflected to actually boring, repetitive behavior, because agriculture, it is actually a repetitive task where you need to go from plant to plant, and also the environment that you have in agriculture, it is not as convenient as you are work in the office, as you are work in the factory, and so on. Because usually in Malaysia, it is so hot, and it is not that comfortable for us to do the work in agriculture. And last one is to compensate the lack of workers in agriculture. So as you all know, the youngsters nowadays, not many of them, I think very just a little tiny bit of them like to work in agriculture. So most of agriculture farmers, most of them are in the age of 14 and above, 40 and above, right? So that they are no apprentice of workers in agriculture. So the lack of workers in agriculture also supports the implementation of robotics in agriculture. Right. So in order for us to implement the robot in agriculture, we also need to understand what are the type of locations that are available for us to grow the plants. Right. So there are 2 types. The first type is open field, where you can see when you are travel to your hometown and so on, you can see there are lots of open fields. All right. And then we can also plant our grow our plants on inside the greenhouse. All right, where the greenhouse is actually becoming a popular choice, because we are able to provide an optimal environment and nutrient for plant growth, right? So in the greenhouse, we can control the environment. For example, if it is raining, all right, our plant will not receiving excessive water, because we have some roof in the greenhouse, right? And in addition to that, the greenhouse can also enable the pest prevention, where any insects, it cannot simply go through your greenhouse, because it is an enclosed area where your plants can grow optimally without any interactions or without any other disturbance from the pests. All right, so right now I will introduce the first project that I've implemented. All right, so this project, I think that all of the project inside this presentation, we are doing it together with Associate Professor Dr. Shifila. Right, so the first project is actually regarding the multi-objective navigation system for agriculture mobile robot. Okay, so this project is actually reflected to the, we call it a disease, okay, where we are, when we are planting the cantaloupe plant. Cantaloupe plant is actually a type of melon, right, that we grow inside the greenhouse located at UTM. We observe there is a disease called powdery mildew. So this disease is actually caused by fungal disease commonly found in cantaloupe plant. It is actually a fungus-based disease, right? So as we can see here, the effect of this disease, it can leach nutrients from the plant. As you can see here, the color of the leaf is already affected. This is the cause of the problem here, right? So when this virus, right, leach nutrients from the plant, it can, we call it, reduce the quality of the cantaloupe fruits, because the cantaloupe fruits get the nutrients from the plants. If the plant is already affected, so the output that we get will not be that good, right? So the treatment that we have to use to treat the plants is actually the affected plant must be sprayed by using pesticide to eliminate the fungus, right? So before the fungus or before this disease becoming outbreak to all parts of the plant, so we need to treat the affected plants only, because we wanted to save resources, and it also reflect to the precision agriculture applications, right? So let me, okay, so this is the system that we use. So we developed a mobile robot, right? A spraying mobile robot that equipped with a pesticide tank, water pump, and also spraying nozzle, because we wanted to spray the pesticide throughout the plants. Right, so this is the greenhouse that we have been built, right, inside UTM. So we have several greenhouses, right? So for the greenhouse, we have planted a cantaloupe plant in a total of 4 main rows. Okay, this is row number 1, row number 2, row number 3, and row number 4. So each row, it has a total of 2 sub rows. So this is the first sub rows, this is the second sub rows. All right, and then from each row, it has the distance of 0.9 meter. And between, we have 4 rows. On row 2 and on row 3, we also have introduced entry points so that the robot can easily navigate from one row to another without they have to finish throughout one long row, and then they can travel to another row. So we introduce entry points at the middle of each and every rows. All right. So how we wanted to solve the problems, all right? So we are using optimization algorithm called non-deterministic sorting genetics algorithm 3, okay? Where we are planning the path of the robots, all right? So as you can see in this figure, so this figure is actually reflected to the greenhouse that we have built. So this is actually the simulated environment, all right? So as you can see, we have 1 row, 2, 3, and 4 rows of cantaloupe plants, right? And then each rows have 2 sub rows, okay? And in the second and third row, we have introduced entry points so that the robot can easily navigate from one row to another. All right. So this figure, it shows that all of the path alternative that the robot can navigate from one point to another. Okay. And as you can see from the red dots here, so it is actually reflected to the location of the affected plants where the robot need to go. Okay. And then from all of the alternative of path that the robot can go, we use NSGA3 algorithm to optimize the sequence of the navigations so that the robot can go from the starting point to each and every plant with a minimum shortest distance and also minimum routing angle. All right. So this is the path that the robot have been produced from this algorithm that has the shortest distance and also the minimum routing angle. And during this navigation, we also considered a similar start and end point. So the robot must start and end at the same point. And we also considered the tank capacity so that the robot can spray to all parts of the plant optimizedly without consuming much energy and much power. All right. So during this project, okay, when we are developing the robot, every time we wanted to test the robot, we need to carry out the robot. So as you can see, the size is not that big, but the weight is so heavy, especially when we are combining with the battery, right? So it is not easy for us to transport the robot every time when we wanted to test the robot. So we have decided to develop an environment called virtual greenhouse environment to imitate the actual environment that we have here. Right, so that we can test our algorithm, we can test our control system, we can test our robot structures and so on in the virtual environment. All right, and after we have been tested in the virtual environment and we are sure that the robot can work in the real environment, and then we test in the real environment at the end of the project. All right, so this is actually just the overview of the virtual environment where we can customize our view. So this is the first person view, this is the third person view, and this is the aerial view. So as you can see, the aerial view here, it is being used to create the map for the robot. We just use we call it the virtual environment view to create the map of the robot, the layout of the environment. All right, so this is the simulation that we have done. All right, by using 3 different comparisons of the algorithms. All right, so as you can see here, the simulation right now, it is being simulated. So each and every robot is operated based on the path or based on the sequence that has been given by each and every algorithms here. Okay, and then as you can see here, the NSGA3 will complete it first. All right, and then followed by, if I'm not mistaken, NSGA2, and lastly MOPSO. All right, so we will see. So this is the first completed operations, and this is the second completed, and this is the last one which has been completed. So each and every algorithm is being tested in simulation before we apply it to the real environment, so that we can save some resources, we can save some energy, all right, our energy and also the robots' resources, right? Okay. So after we do the simulation, we test in the real environment. So this is the part of the test where we use the robots to move autonomously without any remote control. We implement inside the controller, and the controller will run itself to spray the pesticide to the plants. So this is the example of the real application of the robots. All right. So now let's move on the next project. Okay, next robotics implementations of project 2. So this project is called Greenhouse Environment Mapping using a low-cost LiDAR via robot operating system. Right. So basically, when we see in the previous project, the environment that we use is actually based on the simulated environment, right? But sometimes when we do some modification inside the greenhouse, we wanted to create like a mapping which is very dynamic. So it is easy for us to create a map for the robot, okay, dynamically. So we conduct the second project where we will do the mapping, the real mapping of the robot by using some hardware. Right. So the problem statement for this research or this project is actually usually expensive sensors are used for agricultural environment detection, thus limited the commercialization of agricultural robots. So basically, when we are talking about agricultural robot, they are using a very expensive sensors, right? Therefore, an inexpensive sensory system for agricultural environment detection is needed for agricultural mobile robot. So when I do research attachment, they are using a very expensive sensors for the mobile robot. But the application of the sensors is just a basic, just for obstacle detection. But they are using a very expensive sensor for that. For example, this is the SIG MRS 1000 LiDAR, so which is cost for about 3,689 USD. And also this is a 6 LMS 100 LiDAR, which is cost for about 4,882 USD. So this sensors is very expensive. It is just one sensors. So when you combine with the robot structures and another sensors, and the price of the robot will become much more expensive. And it will limit our farmers to implement the robots in agriculture. So we need to have a very not that expensive but not that cheap sensors. All right, so what do we use or what do we implement in this system is we are using RP LiDAR A1, which is actually cost about 1,000 ringgit. I'm not sure how what is the currency, rupiah currency for 1,000 ringgit, right? So for this system, we are using the Intel Core i7, okay, notebook that run ROS and in Ubuntu 16.04. So, and the base platform that we are using is the mobile robot with the Turtobot platform. All right. So how does this LiDAR can create the map of the environment? It is by using the sensory data, we call it the light sensors, the laser sensors, which has been rotating in 360 degrees, right? And then from there, it will get the data and it will extract the landmarks, right? And then from the landmarks that has been extracted, the landmark is extracted by using the scanning methods. So the scanning, the LiDAR will scan the environment, and if they detect an obstacle and if they detect something, they will register as a landmarks, right? And then it will associate the data, right, in two forms. All right, so the first one is it will associate the data by using the match landmarks to the IMU sensors. So we also have localization sensors on the robot to localize the robot inside the environment, and also to predict the map and robot state. What is the angle of the robot? What is the we call it the things which is in front of the robot, and so on. All right, and then it will be matched by using LiDAR, and then the LiDAR will also produce new landmark, okay, to insert the generated map inside the environment. Right. So as we can see in the previous presentation, so this is a simulated area view, and this is a map generated from the previous implementations. Right. So when we implement a real robot, so this is actually the map generated from RP LiDAR. Right. So as you can see here, the line of the edge of the greenhouse is not that smooth. So it is actually mainly it is because of the surfaces inside the greenhouse. It is not even. It is not like in the office. The office, the surface is so flat and the robot can travel, all right, smoothly without any interference. But inside the greenhouse, the uneven surfaces, it will affect the localization algorithm, it will affect the IMU, it will affect the encoders, and those things will affect the quality of the map that has been produced, right? And as you can see here, they also have the, you know, the light that is escaped throughout this edge here, right? So this is mainly because of the surface or the wall of the greenhouse itself. It is actually semi-transparent because we wanted to get the light from the sun, right? So the structure or the material that we use at the wall of the greenhouse is semi-transparent. So sometimes the light from the LiDAR, the laser, we call it uh, the laser spectrum, can escape from the semi-transparent. So that is why they registered as non-obstacle. That is why they have some escape. We call it blue line here, blue surface here. All right. Okay, so this is actually another part of the project. So for this project, we are designing actually a line following robot inside the greenhouse. Okay, so to detect the line, what we are using is we are using a vision system. We detect the color of the line, and also we are also using we call it QR code as a local localization for the robots, so that the robot could be able to navigate autonomously by referring to the line and also by referring to the reference of the QR code. So let's watch the video. So as you can see here, this robot structure, okay, it is actually being developed, all right? Okay, as you can see, we have two cameras. The first cameras at the front and the second camera at the back. And we also have the second camera, and the third camera is actually at the side of the robot to detect the QR code. Right, so this is the line that we have installed, all right, inside the greenhouse environment, and each plant has their own QR code. So it means that now the robot knows where it is at, because the robot are able to identify the plant ID by using the QR code, right? So actually what I can say, this experiment is actually a success implementations where we are able to navigate the robot autonomously, right, by using vision systems, right? And the robot will be able to follow the line and follow the instruction that we have by scanning the QR code. So if you want a robot to go to the specific plant and then to spray the plant, so when they scan the QR code, they will spray the plant. So because they are now we are at this plant and we need to spray the pesticide. Right, so this is another implementations of automation in robotics, but we implement it inside the greenhouse. So we use the line following and also the QR code methods. Right, so this is the third part of the presentation today, where I did a research attachment at Kyoto University, Japan. Right, so in this attachment, I've been supervised by Professor Michi Saida. All right, so it is at the Graduate School of Agriculture, Kyoto University. Okay, so what I've done here, because I just go for about a month, so it is not I've not done much here because we have a very limited time. But the implementation of robotic that I can see in these implementations, they are implementing we call it a tractor, okay, a rice transplanter. They wanted to automate the process of transplanting the paddy plant or rice plant, right? So rice transplanting process, in this technology, they are using the DGPS transmitter. All right. So the DGPS is actually differential GPS, where it is actually a GPS application, but it is not as we call it it is not similar to the normal GPS, where in this DGPS application there will have a station. Okay, so this is the base station, right, where the DGPS base is being receiving the, we call it the data from the satellite. Right, so the satellite will send the GPS data to this workstation, and then this workstation, it is acting like the local GPS. All right, and then there is another GPS antenna here. So this GPS is being connected to the base only. It is not being connected to the satellite version of GPS. Right, and this is they also have a LiDAR sensor here, 6LMS5S500. All right, so this is LiDAR sensors. It is used to detect the at the end of the or they just wanted to detect the border of the paddy fields, right? And then they also have a marker here. So the marker here, it is actually acting to mark the middle of each plant, okay, each paddy field, each paddy rows, to ensure that the paddy transplanting process are done correctly, right? And then they also equip with IMU, and they also have a PC to process the data, and they also have a router inside the rice transplanter, right? So this is actually the videos where they conduct the rice transplanting process. So they also have a drone to record the data that to record the transplanting data that they are as they are experimenting. So in this application, they still need an operator to be at the rice transplanter because it is still in experimental stage. Right. So now, when they are doing the experiment, right, the things that the problem that they have is, as you can see here, there is inconsistent line. Because this is actually mainly because of the structure of the soil itself. As you can see here, in the paddy fields, the muddy structure, the uneven structure, it will make the rice transplanter to become to produce this one lah, inconsistent line, because sometimes it will be diverted a little bit because of the muddy and so on, right? And then the second problem is there are some blank space, right? So each paddy plant, they have a fixed distance, and they need to fill each and every parts of the rows so that there are no blank space between each plant. So we need to go down the fields and we need to fill up ourselves, right? So this is the problem that we face, and then right now they are still solving this kind of problem. All right. Okay, so for the conclusions for my presentation today, so robotics also plays an important role in agriculture because I'm sure that there are lots of applications in robotics, such as in we call it manufacturing industries, all right, and also in safe and rescues and so on. But in agriculture, it is had a lot of potential that can be applied, right? So as the agriculture areas are quite subjective, so the application of robotics is becoming harder to be implemented because every environment has their own elements. Every environment has their own pros and cons, their own factors and so on. However, as the advancements of technology has been developing rapidly nowadays, so I'm sure that, and I believe that the technology nowadays are able to solve the agricultural problems effectively to help the farmers to manage their crops. So I'm sure that some advanced technology like deep learning, right? And as you can see from the prestigious university, they already have like a very good structure of robotics, and they can solve, I'm sure that they will solve some of the agriculture problems in the futures. Right. So I think that is all from my sharing session. Right. Thank you very much. If you have any question, please don't shy to ask. Right. Thank you, Prof.
Okay, thank you, Dr. Saiful, for the presentation from our first speaker. So I open is there any questions from the audience? We have Azura. Any questions from the audience? Okay, I start first since there is no question. So I want to ask two questions to Dr. Saiful. Since the LiDAR sensor that you mentioned in your slides. The price is about 3 to 4,000 USD, which is I think it's quite expensive. Okay, to apply in the robotic system. So, what is your approach in order to replace the expensive sensor in your study?
All right. So actually previously when this is actually in different applications. All right. So where previously what I've did is I've implementing, we call it visual SLAM, where we use the cheaper version of LiDAR, and then we combine with the visual, we call it visual perceptions from the monocular camera. So from there we can imitate what the expensive sensor can do. So actually the expensive LiDAR is actually, we call it 3D LiDAR, where they can measure 3 dimensions of a structure. So by using the visual SLAM or visual SLAM, right, we can imitate what the expensive sensor can do. But for the cons of that approach is we we may have a little bit expensive computational complexity lah. So we will need more advanced computing technologies.
Okay, my second question is, since we want to apply this technology in our study, of course, there is a uncertainties factor. One of the uncertainty factors that I observed from your visit at Japan is the uneven surface area. Okay, when you want to plant the paddy, some of the pictures there, the paddy is not straight line in the matrix row and column basis, but there is a corner over there. So
Yeah.
what is your approach in order to overcome the uneven surface during planting?
Right. So what we have observed during the visit, so the robot actually the rice transplanter actually moving continuously, all right, without any interference. So for example, when it is an uneven surfaces, they just go back. It is like controller, right? They goes diverted from the, we call it, from the correct road, okay, from the straight line. It will go back to the we call it to the correct rows. But the approach that we can do is that maybe we can introduce some stopping criteria where the rice transplanter, right, it start diverting. I think the robot need to slow down and stop, and then from there, because the diversions factor is actually a very crucial factor inside the rice transplanter, where they diverted and they wanted to go back to the right rows. The trajectory there, it will create a very wide areas of diversions. So I think when the robot starts to divert it, maybe they can introduce some stopping criteria. The robot need to stop, and then they need to go back to the direct rows immediately without continuous moving. Because if it is moving continuously, the trajectory will become wider, and the diversion will become much more bad.
Thank you very much for the explanation, Dr. Saiful. So any questions from the audience, please? Is there any one or two questions? Okay, if there is no questions, so I would like to thanks Dr. Saiful for the very impressive presentations. So I wish you all the best with your studies and research. So thank you very much. So our second speaker is Dr. Muhammad Rizwan. Unfortunately, Dr. Muhammad Rizwan is unable to present and to join us due to his commitment as the Robocon team leader at Cambodia. He's having a line problem over there at Cambodia. so he's unable to present his presentation entitled Robotics Application in Robocon. So due to that, I will invite the third speaker to replace Dr. Muhammad Ridwan. So the third speaker is Dr. Muhammad Shukri bin Zainal Abidin. Okay, Dr. Shukri, you can share your slide. Okay, so let me introduce to you Dr. Muhammad Shukri Zainal Abidin. Dr. Muhammad Shukri Zainal Abidin is our lecturer, our associate professor at the Department of Control and Mechatronics Engineering. Dr. Muhammad Shukri Zainal Abidin, first degree, bachelor degree in mechatronics from UTM, and then master's degree by research in mechatronics as well. And his PhD is from Tokyo University of Agriculture and Technology in the field in the specialization in robotics application in agriculture system. So without any further ado, I would like to invite Associate Professor Engineer Dr. Muhammad Shukri bin Zainal Abidin to present his current research study entitled Robotic Application in Oil and Gas Industry, specifically underwater tank cleaning robot. Silakan, Dr. Shukri.
Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Very good morning to everybody, and thank you very much to our honorable moderator, Prof. FUA'AD, for giving me this opportunity to share my experience in the robotic application, especially in the oil and gas industry. Okay, can you hear me? I mean, can you also
Yes.
view my slide clearly?
Okay.
Okay, thanks. Okay, just for my brief introduction. So my name is Dr. Shukri, and I am a staff of University Technology Malaysia under Department of Control and Mechatronic Engineering. And then in UTM, I am the head of Agricultural System Engineering Lab. And this group is under Advanced Control Research Group. We name it at ACRG. Okay, I've been working with UTM, I think since 1999, after I finished my first degree, and then continued with my master. And then after some times, I further my study for PhD in Tokyo Agriculture University, Japan. And basically, my area is now related to agriculture engineering and also agriculture system. But somehow also involved with some of the robotics works. And as introduced by our first speaker, Dr. Saiful, Dr. Saiful was my my previous student, right? So during his, I think, undergraduate, master, and also PhD. Okay, let me continue with my research work. Okay, for the introduction, so basically this project is an industrial project which initiated somewhere in 2017. And then since then, we still have ongoing work in continue to develop this robot with some new features and also improvement. Okay, just for the introduction. So this industry name is called Maidaris and Safety Sdn Bhd. And then the business of this company is related to confined space specialists. And maybe some of you is not familiar what is a confined space is. And then if you look at the figures on the right, so you can see these workers are working with especially tanks. And then in this first image, you can see they are collecting some data related to the gas content of inside this tank. And also it is related to some of this cleaning work inside hull or inside this tank or inside this mixer. And then they have to do maintenance on also removing of the unnecessary sludge. And then here also, I mean, when dealing with this kind of operation, they have to wear all these PPEs and so on, right? So basically, this area is called a confined space. And then this area is basically very hazardous and very high risk whenever some kind of work or maybe activity need to be done there. So for this reason, any activity that related to confined phase must involve with worker or personnel that is authorized or competent, right? So this company is also, instead of providing the service, they also providing a personnel for, or maybe inspectors to do supervision or supervising work for this kind of activity. So this company also related to activity training and also rescue operation, and also they provide some equipments for rental. Okay, with this company, with the project that we involved is development of underwater tank cleaning robot. Okay, basically the requirement for tank cleaning, mainly for water reservoir in Malaysia, is governed by the government, right? So under the National Water Service Commission. So whereby under this commission, all the tanks, all the water tanks especially or mainly, need to be maintained or need to be cleaned at every 6 months. So based on these regulations, all water tanks, especially the reservoir, so need to be maintained by the utility company. And then this activity will be inspected or will be audited by this commission regularly. So in Malaysia, we can find the typical type of reservoir, which is two. The first one is elevated water tank, which you can see here, and also the groundwater tank, which is located on the ground. And the cleaning for this water tank is done manually. So you can see here, this figure, right? So this is called open score, whereby the water in the tank need to be emptied, and then workers will come in and to do the cleaning work. The other method is called closed score, whereby you can see here divers is being deployed inside the water tank, and you can see the cleaning work is done with the water is still inside the tank. And because of this activity, there is a requirement, a new requirement by the government to enforce or to ask the companies to use a robotic application, right, for the cleaning work. So if you look at here, the conventional way of water cleaning, so as you can see from the previous image or the previous figure, so what we can see is that the water inside the tank need to be emptied. And after that, then only the operators or the workers can enter to do the cleaning work and to remove the sludge manually. So because of this, we understand that the water supply will be cut for some time, and then this causes a lot of problems to affected consumer, mainly the industries, right? But then if they use the alternative method to use human divers to remove the sludge, So mainly this will cause a higher cost and also higher risk. And this also related to many of the issues on safeties. And this is why the new method of cleaning using robotic application is recommended by the authority or the government. So the companies that doing this cleaning job need to start to apply or use robotics in their cleaning work. And then if you see, using robotic has a lot of advantage, right? So basically, we can avoid the water supply cut, and then the wastage of water during the cleaning work. And then if you see, this reservoir has different type. The one that which is critical to be emptied is called a primary service reservoir. So mainly this kind of reservoir cannot be stopped because it actually supplies water to the secondary reservoir. So apart from that, you can see that the advantage of using robotic cleaning is to reduce, it can reduce the laborers' work and also high costs in manual tank cleaning. And the most important reason is to increase the safety in confined space work. So you can see in my slide earlier, right? So when we deploy human in this confined space, it affect or also related to many issues, mainly on safeties, right? And then you need to also employ workers or staff that has the competency to work in confined space. And then by using the robotic solution, so it allows non-restricted time frame, because when we deploy robots, the reservoir is still in operation, meaning that the water is still there and it can continue supplying water to the secondary tank or to the customer. And then also that you can see by using robotics, we can do the monitoring and measurement of the amount of removed sludge. And then also the most important here is we can measure the one that we call as NIW. So NIW is a non-income water, because when we do online cleaning or robotic cleaning, we can use a meter, a flow meter, to measure how much water that we remove in order to do the cleaning. And this is important for the auditing purpose. And then by using the robotics application, it allows real-time visual tank inspection or from the recorded video for structural maintenance, right? Okay, so this is how the robotic tank cleaning system works. So you can see here, right? So this is the robot that has a cleaning mechanism, a suctions, and a brush is attached to this robot. And then this robot usually is deployed in the water tank, and it will move along the tank floor to do the cleaning. Okay, so this robot has cables connected to the surface, whereby on the surface we have controllers, and then we have flow meters and also a water pump to remove or to suck the sludge on the tank floor. Right. So, and then usually this robot is deployed through a hole or manhole that usually builds on the top of the reservoir tank. Okay, so this work basically start with what we call as the first version robot. We call it Robot 1.0. So the first time we start collaborating with this company, they already have or they already using this version of robot. And then when we start to work with them, the first thing is to upgrade this robot, because they have so many problems with the previous robot. And then from there, we come up with robot 2.0. So, and then from this 2.0, we try to have a new design, right? which has a lot of improvement based on the first design. And then finally, we have the third generation of the robot. We call it a robot 3.0, right? So for the robot 3.0, of course, we understand many of the issue earlier, and then we have to do a lot of redesign work, improvement on the component and so on. Okay, so little bit of background on the first version of the robot. So this is how the robot looked like. It's a bit bulky in size, and then most of the components are not very reliable, especially to be used in underwater operation, right? So we do a lot of troubleshooting, and also we investigate the cause of the problem. And then from there, we start to understand and we propose a newer design of the robot. So you can see, so this is the, the replacement or the components that we upgrade from the first version of the robot. And then we try to deploy this robot again, and then we still have a lot of problems, even though some of the component has been upgraded. So if you look at the specification of the robot 1.0, so mainly the problem arises because of the weight of the robot, which is too heavy, and then the size of the robot is too big, right? So because of that, you can see some of the area, some of the manhole that we need to deploy the robot is too small for the robot to enter, right? So the requirement that is asked by the company is to design a newer version of robot, which is smaller so that it can easily access this air well, and also to reduce the weight so that it can be easily handled by the operator, right? Okay, so besides having requirements from the company, we also have a mandatory or important requirement by the utility industry, right? So our collaborator or the company is working close with one of the utility industry called Shabas, right? So Shabas is the water utility provider for Selangor area. And based on them, so these are the things that need to be considered in designing the new version of the robot. So basically they are concerned with the type of material used, and then the hygienic of the robot, and also the operation time. And then they are also concerned with the sediment and debris size that the robot can clean. And also what about the recording and reporting method. And then they also ask for mapping, and then the requirement of water lifting capacity, the cameras, the quality of the video, the size of the robot. Again, they also mentioned about NIW, and they also ask for autonomous robotic cleaning, right? And then the lighting, and then the distance of the robot to the opening or to the manhole, right? So since we have this requirement, I mean, in Malaysia, just for your information, the application of robotic in underwater cleaning is very new. So meaning that we don't have any uh, regulation yet, right? So different authority will provide different requirements for their application or for their operation. So basically, this is also one of the starting point for us to define this specification. Maybe in future it become a standard for all the operators to comply whenever they have activity related to underwater tank cleaning, right? Okay, so this is the the new specification that is proposed in the newer robot 3.0. So you can see these are the specification that we propose, and we design or put it in our design for the cleaning operation, right? So we try to meet many of the requirements leased out by the authority and also leased out by the industry, right? Okay, so you can see that this is the design for the newer robot, the latest one. So this is the body, right? And then this is the cabling junction box, and then this is the piping system for suction, and then the wheels, and we also have a newer design of the controller and so on. Right? So this is how the robot look like, right? And so we do testing and also commissioning of this robot, right? So firstly, we test it in the lab, and then we bring the robot to one of the reservoir, and then we deploy it in the reservoir tank. And these are the operators that doing the deployment work and also the cleaning for commissioning this robot. So you can see that this is how uh, the reservoir tank look like inside, and then this is the surface of the reservoir floor. Okay, this is the final design that we completed. So you can see that it's made of stainless steel, and then it has cameras, lighting system. It has also the suction brush, the the piping and so on. This is an outlet that goes to the uh, surface water pump to do the suction of the sludge. Okay, this is for your information about the ground reservoir layout. So this is one of the reservoir tank that available in Johor, right? Okay, you can see on the top of the tank there are a few air well, whereby this air well is quite small, but then it is important because in some operation, so we need to deploy the robot through these air well holes, because if we if we only rely on the manhole, sometimes the manhole is far from the area that we can do the cleaning work. So sometimes we need to also deploy the robot here in through the air well. Okay, for this design of a ground reservoir, so if you're looking at this structure design or structure drawings, you can see this is how the tank, the reservoir is being built. So the main components for this reservoir is the pillars, right? So they have many pillars. So this pillar is used to support the roof of the reservoir, and also you can see these are the air well, and here you can see the manhole. So this newer design of reservoir, they provide stairs for maintenance, right? Okay, so usually when we want to do the cleaning work, so we have to do uh, planning, right? To understand the location of the pillars as well as the location of the air well and also the manhole, so that from there we can decide where to deploy the robot for the cleaning operation. Okay, so this is how we deploy the robot, right? As you can see, because of the robot weight is not very heavy as the first version, so we can deploy the robot manually, and then once the robot is being deployed, and then we can start to do the cleaning by using the uh, the panel with some controllers, right? Okay, you can see that this is how the underwater robot works, right? So you can see this is the water inside the reservoir tank. So this is the pillar, and this is how the robot move to do the cleaning, right? So you can see here, this is the remove sludge that is being removed from the reservoir floor, and this is how uh, the the camera on the robot shows. And the left is the area where we already do the cleaning, and the right is the sludge that we need to remove. Okay, so this is the performance. Okay, since this robot is not yet autonomous, right? So we have to move the robot manually using the pendants. And then since the robot has no mapping capability at this point, so it is important for the operator to do the planning and mapping manually, right? So basically for this case study or for this cleaning operation, you can see this is how we build the map. And then from this map, we plan on where to deploy the robot. And also we do some recording on the area that we clean, right? So you can see from this area, so there are a lot of pillars. And then based on these pillars, basically we do the planning for the cleaning, right? And then usually for 1 day work, we can clean maybe up to uh, 4 to 6 cells per day, right? Depending on how bad is the dirty or how bad is the sludge that reside on the reservoir floor. So here we compare between the two robots, the robot 2.0 and also the robot 3.0, right? So basically for this project, uh, we are required to complete the cleaning work within 27 days. But what we have done, we completed the cleaning work only within 70 days by using the two robots, robot 2.0 and also the robot 3.0, right? Okay, of course, for the performance evaluation, we can understand that the robot 3.0, within the same time period, it can complete more area compared to robot 2.0. So of course, for the robot 3.0, we have to do a lot of improvement for the cleaning operation to be more efficient and faster, right? Okay, so what we are doing right now, instead of building the robots and improving the design, we also try to work on optimization part. So meaning that when we look at the map of the reservoir floor, and then this map also contains the pillars. And as you know, that the pillars is important for us because the pillar guide on how the robot to move on the reservoir floor, right? So what we did here is that we tried to deploy the algorithm, the method for optimizing the route plan for the robot to move around or to deploy, because the robot has cables and also hose that it carries from the surface, right? So we have to make sure that this robot, this hose or cables is not tangled around any of these pillars, so that the robot will become stuck. So it is important for us to design or to plan the cleaning path carefully uh, to avoid this problem and also to optimize the cleaning process, right? Okay, so this is I shared to you the videos, right? So this is how the robot move on the visible floor. So you can see this area, the white area is where we already do the cleaning, and this black area is the sludge that we need to remove, right? So now you can see how thick the sludge is, and this robot has to remove this sludge uh, as fast as it could. And then this is how the robot start to choose its path and also to start to do the suction and cleaning of the sludge, right? So you can see I move the video faster. And then here you can see the robot arrived to the one of the pillars inside the reservoir tank. So this pillar, as I mentioned earlier, is important for us to guide the robot because we don't have any sensor used for mapping and also for detecting obstacles. So everything is only rely on the camera itself. So the operator must have some skills to understand the environment and to decide on the path for the robot to do the cleaning. Okay, you can see here after arriving at the pillars, the robot will turn around and continue to remove the remaining sludge. And the movement of the robot is like a zigzag, right? Zigzag. So as I mentioned in the previous slides, so it's important for us to plan the cleaning operation, right? So that we can do the cleaning work effectively while maintaining the safety of the robot and so on, right? Okay, I will also share to you some videos related to, okay, so you can see here, right? So you can see here, there is also area where some of the reservoir floor is missing, right? It's missing. So that's why one of the advantage of using the robotic application is for structural maintenance. So meaning that while doing the cleaning, so we also can do inspection whether the structure has some damage or need to be repaired, right? And then you can see this is the dirty or the sludge that is being removed from the operation or from the cleaning, right? Okay, I like also to share some of the view taken by using ROV to see how the operation of the cleaning works that is being conducted in the reservoir tank, right? So this is when the robot is being submerged into the reservoir tank, and then it arrived at the reservoir floor. So this this video is taken from the robot itself, right? So you can see once the robot arrive on the floor, the debris start to fly off, and then that is important where this time we need to start to pump the sludge out so that we can have the robot can have a clear view of the path in front, right? Okay, now this is how the robot move and when it start to do the cleaning, right? Okay, so this is the clean area and this is before the area being cleaned. So because for this tank, the sludge is not as thick as the previous tank, right? So this is for testing. And then you can see this is how the robot move and the robot work on the cleaning process, right? So basically we cannot move the robot too fast because sometimes we have a very thick sludge, right? And then it needs the robot to move back and forth to make sure that the sludge is completely clean, right? So the operator must have some experience on how to maneuver the robot. Okay, you can see here, because of the dirt is not so thick, the water is not so dark, right? And then here we can have the data in terms of the NIW water that we need to measure when we do the cleaning work, right? Okay, I think that's all for my presentation. So maybe if you have some question, you can ask me after this. So back to our moderator, Prof. Mat.
Okay, thank you very much, Dr. Shukri. Very interesting presentations. Okay. So I open the questions to the audience. Is there any questions from the audience?
Prof Fuad dengan
Yeah.
Prof Fikri ya.
Ya. Silakan, Syafriza. Okay.
Ya, saya daripada Universiti Malaysia Perlis.
Ya, silakan.
Terima kasih. Just nak tanya satu soalan saja, Dr. Syukri. Tadi ada maklumkan robot ni belum autonomous lagi kan?
Yeah.
So macam mana handle tangle wire, tangle suction flow apa semua tu, sebab kalau dia pergi jauh dia macam ada multiple lines of connection from operator to the robot kan?
Yeah.
Okay, terima kasih.
Okay. Kalau kita if you go back to the slides, right? Okay, I share the slide again. Okay. Okay, so if you look at this slide, so this image. So basically when we deploy the robot, because the robot has cables and hose and so on, right? So we use this floater to carry the robot all the way from surface to the robot. So basically this is the robot, right? Okay, the first thing is the operator must have the experience, right? Experience in terms of understanding how the reservoir is being designed. As I mentioned, we have a lot of pillars, right? So that's why when the robot is deployed, maybe start from a manhole. So from there, the operator should understand the path carefully, because if the robot is to be moved on one direction, so he has to make sure that the robot return through the same path that it start earlier, right? So this is how it's done, because we don't have any other way to understand where the location of the robot inside the water tank, because the water tank is very dark. So if you look at the robot also, we have a beacon. This green color is basically the beacon. So basically the operator, whenever he has some problem to know the location of the robot, maybe he has to look down inside the opening so that he understand where the location of the robot in the water. So as I mentioned again, so the robot, the operator must have some experience, right, to understand, because that's the only way, because the robot carry a lot of stuff together, the hose and also the cables and also this marker. We can also consider this on the cell. The cell is the area within the pillars, right? So after finish one cell, it moved to another cell. And then this is done consequently until the whole area is finished. That is why this mapping is important, right? So that they know how to move the robot and which area to move and which path to follow, so that the cable is not being tangled anywhere. So thanks.
Okay, thank you, Dr. Shafiza and Dr. Shukri. Any more questions from the audience? Okay, I have one question, Dr. Shukri, as the moderator. One simple question: since this robot is working underwater, so there is a high pressure from the water itself to enter to the robot that working in the underwater. So what is the steps and precautions to avoid this high pressure and water enter to the pump system?
Okay. Okay, let me share this slide again, right? Because we when we start to design the robot, right, basically we we need to consider that because the buoyancy is very important, right? So, so meaning that the design of the robot is also important because we don't want the robot to float or to float on the water surface or in between, because this robot must all the time reside on the floor. So that's why if you look at the design here, right? So this robot is not totally enclosed, right? Because you can see the robot has many holes. So many holes meaning that water can come in, can penetrate the robot body, right? So the buoyancy for this robot is very small, so that it can reside on the floor at all the time. So that's why, I mean, when we design the robot at around 70 kilogram, so once the robot is deployed in the water, so the mass become lighter, maybe like 13 uh, to 14 kilogram. But still, we have to make sure that the robot reside on the reservoir floor. And then once we start the suction pump, so it's like a suction force that maintain that how to say that put the robot or maintain the robot, the contact of the robot to the floor, because we have the suction force that force the robot to based on the gravity and so on, right? So basically, this is how we do the manipulation of the robot mass on robot design in order to make sure that the robot stays on the reservoir floor to continue the suction and cleaning work efficiently, right? Because we don't want to sacrifice the mass, because if you look at the process, right? I mean, everything must be done manually, meaning that the deployment and everything. So we don't use any cranes to deploy the robot. It means that the robot is lightweight, but not because the lightweight that the robot floats, but still it can remain on the reservoir floor to do the cleaning work.
Okay, thank you very much, Dr. Shukri, Zainal Abidin. So we wish you all the best, okay, for the further research in that field.
Thank you, Prof, and thank you everybody for your time.
Okay. So our final speaker will be Dr. Sofan Wahyudi. So Dr. Sofan Wahyudi can enter your Zoom and share your slides. Let me introduce to you Dr. Sofan Wahyudi Nawawi. He's Associate Professor at the Department of Control and Mechatronics Engineering. So Dr. Sofan, bachelor degree, master's degree, and PhD degree is from UTM respectively. Currently, he's engaged in the balancing robot and drone system using a control technique. So without any further ado, I invite our final speaker for today's webinar, which is Dr. Sofan Wahyudi. Silakan.
Bismillahirrahmanirrahim. Assalamualaikum and very good morning to participants, and thank you very much for a very nice introduction from Prof. FUA'AD, our moderator today. Without further ado, I'm Dr. Sofan Wahyudi bin Nawawi. So like just now, Dr. FUA'AD shared to us that my degree until PhD is from UTM. So actually the titles for my sharing today is a control techniques in balancing robot and drones. So it comes from the idea of my PhD in 2005 last time when I started my PhD. I'm doing the balancing robots. Then currently I'm doing some works in drones. So that's why today I'm going to share with you guys about the balancing robots and drone and how to control it. Okay, so next. Okay, so this is my presentation layout. First, I'm going to introduce about main components of how to control a balancing robot and drones. So next, I will show you the details in aspect of balancing controls, balancing robot controls, okay, by modeling the mathematical model to get the what we call as motion equation for the robots. So next, we show you how to do a controller design, then fabrication of the robot for verifying our algorithm or controllers. Next, I will go the last part, which should be in drones, where it's actually a simulus method. Then I will show you some features of the control in drones. Then finally, the conclusion. All right, here is the component. Here is the component of the control for both system. Okay, where we have here is a balancing robot, as you can see here, and here is the quadrotor, where we can call as a drones. All right. So the first part that what we need to do to realize the control scheme in both system is actually we need to find the mathematical model for both. Okay, so so here is actually the common method where from the mathematical model of the systems we can have something like a different method. For example, by using the first principle like Newton law. Okay, we can find the mathematical model. We also can use other method like Lagrange equations, so all that is based on the is all based on the mathematical derivation and so on. But they have others method. If we get the hardware before we do a designing, so if you get the drones or balancing robot, okay, then we can test it. We can put input and we can measure the output, so that it can be also done to get the mathematical model by system. We call it system identification. So I think FUA'AD is very good in system identification. So we have the transfer function from that, where we also can have the what we call as the motion equation for the robot. So next, after we done that part, so we go for the controller design. So here we have a lot of controllers where we can apply. They have a linear controller. They also have a non-linear controllers. So you can choose which one you want to explore it. All right. So after we design it, okay, controller should be based on the motion equation. So finally, we can do the simulation work to test it before we can do for the implementation later. So maybe by using a MATLAB simulate and etc., where you can test it to make sure your algorithm is in order. Then finally, okay, we have the hardware for fabrication. All right. So last one, this is the last part. Actually, we can do the fabrication of the robot so that it will follows all the parameters where we set in our mathematical model in the first stage of the designing. So from that, we created the mechanical part of the controller to be a test bed to the system, so that we later on we can do a verify or comparison from the simulation and the experimental. Okay, so let me go for the first part of this sharing, where I'm going to discuss in details on the balancing robot. Sorry. So the basic idea for the balancing robot, or I always call it as a two-wheel inverted pendulum robot, is okay, it will drive the wheel in the direction so that the robot want to handle the pole here. It should be not falling down. Okay, so that's why this robot, which have two wheel, okay, will move forward and backward so that it can balance the poles. Okay, so it should be the input. They have two input for this kind of balancing robot. For the first one is maybe right wheel, then the second one is for the left wheel. So it need to be moved so that it need to be balanced on the first place. Okay, if not, it will falling down. So actually, this kind of robot is find interesting because many researchers have applied these ideas for various problems like designing, walking gates, for example, for humanoid robots. And then we also have the robotic wheelchair where the wheelchair can climb the stair, for example, and also we also have like a personal transport system. Okay. Okay, here the example of the balancing robot design in a different way. Okay, as you can see here, we have the N-board design. Then the second one we call as a Joe balancing robot, where they develop in labs to to see how the implementation of the inverted pendulum system can be implemented to the balancing robot, so it can make more interesting application. Then here the last one, I think everybody know about the Segway. Okay, this is designed by Dean Kamen. I think it's the same time in last 2005, but he only focused on the human transport. In my time, 2005, he also doing the same times with me, but he focused on the human transport. The application of a very simple controller like PID to be implemented into this kind of robot so that it can be balanced easily. All right, so here's the methodologies where I'm going to share to you that how we are going to model, how we are going to have the the hardware part, how we're going to have controller parts. Then after we get all together, so we need to have the method where we can prove the stability of the system. So here, that's why I put here. Okay, we need to use something called Lyapunov method, so that we can prove that by mathematical equation, so that the system can be secure, can be say that it will completely stable. Okay, so then from that we are do a simulation by using a MATLAB simulations. Okay, after verified by simulation, we are doing we apply that algorithm to the real hardware where we call as a test bed. Then from that we do the analyze, we do the result analyze and compare the results. Okay, here is something where we use to model the balancing robot. So as you can see here, I'm using a Lagrange method to do the equation or to get the motion equation. So it's this actually you need to follow the rules of Lagrange method to get the motion equation. Okay, so I don't want to go for detail for this. Just want to show you from that model or methods we can obtain the mathematical equation or motion equation of the robots. Then we arrange that to get the state space form. Okay, so here is the final equation, which is very detailed here with all the parameters. Okay, so from that state space equation, from that state space form, we formulate it. Then why we need to get that? Because it's much easier for us later to design a controllers, and to before that we need to check the condition of the model before we can proceed with the controller design. So here, that's why for my case in balancing robot, I need to check how strong, how we can assess in the state, because just now we have 7 state here. You can see here we have a 7 state where we are going to focus on. Okay, so the main state where we need to have is actually need to be tested before we can proceed to design the controller. So that's why it's come for the strong accessibility condition testing and maximum relative degree testing. All right, so by some rule or properties where we can check it very easy. Okay, so that from these properties, okay, we can get the system is actually, if it meet the requirement here, so mean is strongly accessible. All right. The next, we need to check what is the maximum relative degree for the system. Okay. So we have suggest two rules here. Okay. By using these properties, okay, we get that the maximum relative degree of the system is 4. All right. So from that, okay, we can see that we have a 7 state. We only can assess 4 states. So means we lack 3 more state. All right. So that's why we cannot apply. So we can conclude here so that we cannot apply full feedback linearization method. Okay, because we don't have a full accessible to the state. All right. So that's why we come for another what we call as a partial feedback linearization, because we cannot get a full. So then we call it as a partial feedback linearization, and the rest we need to change. We need to arrange the form of the state space. Okay, so that we can convert it into the partial feedback linearization. Okay, so here how we're going to change it. All right, so how to make it partial feedback linearization. This is the way how to make it a partial feedback linearization. By using a certain rules, we apply it. Then finally we get the equation of the state space form where it fulfill the partial feedback linearization. Okay, so all this is the arrangement of the equation so that it will follow all the rules and law to make it to be a partial feedback linearization. Okay, so here's the simulation where we want to see either by this partial feedback linearization, is it the robot can be controlled. So when we can see here, we have the increment of the speed and also the change of inclination angle, means the pole moving in a certain value of angle. So when we change the angle, the speed will be different. So we prove it by using this rule by the previous equation. Okay, so now we confirm that it can be controlled by using a partial linearization. So we propose 2 levels, because in a balancing robots, the things first is you need to balance the robot. Okay, it need to be not falling down. It need to be balanced first. Okay, the pole need to be balanced. All right. So that will be handled by, we call as a lower level controller, where I put here a short form LLC. Okay, LLC is actually a very common problem, like the inverted pendulum problems. It's very easy to design a controller due to the linear structure of the new coordinate of the system, where it's always in the controllable form. Okay, so for the higher level controllers, the second part will be activated later by the condition where LLC is settled down. So after LLC is settled down, then it move to the HLC. HLC is short form for higher level controller. So at this part, we are going to control the speed and also the theta of the robots. So where we need to make sure this controller or higher level controllers can be at the stability condition, where that's why we come up with the Lyapunov function, like just now I mentioned in my slide. Okay, at certain part we need to prove it by mathematical equation so that the controller can be proved stable. So that's why I'm applying the Lyapunov function to shows in the mathematical equation, okay, the system is stable at that state. Okay, so because of the changing of the controllers here, okay, when we see the changing of the controller from lower level controller to high level controller, they got something, a very critical part where the control people will always thinking about the stability. When it changed from the LLC to the HLC, what happened in between that. So later on, I will show you the architectures. I think it will be more easier to understand. So this is the structure of the balancing robot. We have a controllers here. So we have a state here, orientation. And then we have a theta D, which is the inclination. Then also VD is the speed of the balancing robot. All right. So here is the lower level controller, which is LLC, where we propose the controller here, okay, by the equation, by manipulating some equation and properties. So then we get this equation, and then is for this one is for the higher level controller, where we consider is a class of the nonlinear system, okay, where it derived from the previous equation with some modification, so that it can be guaranteed to be asymptotic stability when the control law applying to this equation. All right. So this is some short, proof by using Lyapunov function, where just now I say that we have to prove that, so that the system can be stable when we apply this kind of controllers. So we find out that the V dot here, this is very crucial when you finding the Lyapunov function. So V dot should be less than 0. If you can get that, so then means your system is stable. Right. So this is how we do a control structure of WIP in detail. So here is a controllers. Inside a controller, we have a lower level controllers and also the higher level controller. So so that's why this part should be settled first, which is a lower level controller should be settled first. Next, after it's settled, we move to the higher level controllers. All right. So in between that, there's a problem. Okay, there's a problem. So you should think how to settle this problem. So in between, to change the lower level to higher level, in between that, we don't know what happened, right? So so from here, we start to think what kind of solution we have, proof to make sure in between the change of the lower level to the higher levels, we can guarantee, okay, the system or the balancing robot don't fall. Okay, so that's why from other people works, I find out that they have a solution there. So we are using this kind of scheme for the controller. All right, so here is the rules. Okay, when the system moving, so actually in the simple word, we can say that we will change some things so that the real data and the processing data will be a bit slower, so that we can cater that. So they also have something like tuning weightage, so we can arrange that to get the good response of the system when they change the controllers. Okay, so this is how we doing the gains tunings. So we have a 7 here, okay, KA until KV2. So all have their own specific range. Okay, to tune it. Last time when I'm using, a iterative tuning method, it will take around 7 days. By using a common PC last time. Okay, so to get the value of the gain KA until KV7, KV2, so it took some about 7 days. I will get that. So this is what we call as the iterative tuning methods. Okay, when we get the value of gain K, we apply it, then we can say that the robot will follow our requirements based on the controller design. So next is hardware work. So actually this is the balancing robot that we have. The first one is the first version of the balancing robot. Then the second one is the final version of the balancing robot. Okay, so why this robot is very interesting? First, we can say that it can be turned easily on demand. Okay, so it can move around without any space constraint. Then this kind of robot is actually still a non-holonomic types. So what is non-holonomics? What is the difference between the holonomics? It's like, when you see a car, it have a constraint to move. For example, it can only move, a certain specific, direction. So it cannot move in all direction 360. So that's why we call it a non-holonomic system. If holonomic system means the car can be moved in 360, direction. Okay, it can move front, backward, side, left and right, for example. So that's kind of the holonomic, because there are no constraint on the holonomics. Okay, then this kind of robot is actually very nonlinear. All right, to design this hardware, I call it a test rig setup for the balancing robot. So it should have comprised of three main parts. The first one is the mechanical parts. And then we have actuators. This is for the input and also the controller parts. And then the power to to be supplied to the computer, to the board, and so on. So in order to complete the test rig, so they have three goals. Okay, we need to design and build a physical prototype of balancing robot. We need to produce and analyze model in MATLAB Simulink. So then finally we need to run to test it by maybe a very simple one like pole placement controller to make sure the robots can be run. So this is the design of the robot. Actually, with a label here, you can see all the components where we put here in this robot are mentioned here. Okay, we have two motors, for example, here. Okay, we have batteries. Okay, we have the controller box. And then here, actually, we do something like the sandwich method where we put the industrial computer on the top of the controller, motion controller card here, where this motion controller card applying DSP on that time, DSP and the FPGA methods or chip, so that it can do a very high processing, response. Okay, we also have on that time is we call as a DSpace. So DSpace is a motion control card where it collaborate with MATLAB, where on that time we get the the toolbox for the DSpace, but very expensive. It's very expensive. Okay, so in my case, we create by our own toolbox for this controller card, where we can link it directly to the MATLAB Simulink. And from that, we can control this robot based on the requirement. Okay, here is how we control the robot. As you can see, just now I mentioned about the controller card here. This is a embedded controller card where implement the DSP and FPGA technology on that time. Okay, I'm also have something like a data acquisition card here. All right, so this is the gyroscope sensor to detect the inclination angle. Okay, then I have here LCD touch screen. All right, so to control the motor, I'm using the motor driver IPM 100 model because it have I think 20 ampere current where it can generate from the card. Then it can have a very good torque to move the balancing robot. Okay, all together, all the data which will be collected, then pushed to the FPGA card here, which motion controller card. Then it will start to be processed in MATLAB in the industrial PC. So the MATLAB will process all data. It should be a very fast, it should be a very sub-second response. So that because we are applying the real-time system control, so the processing should be in sub-second. So that's why on my time we are using industrial PC. So very small factors of PC, but we installing the I think Windows 8 on that time. Okay, we installing the Windows 8. Then the Windows 8 also, we have a layer, in Windows we have a layer, first layer, second layer, I think maybe 7 layer. Some of the layer need to be removed so that we can do the application of the real time. So some of the layer need to be removed, okay, before we can do the application for this balancing robot. It's not straight away use a Windows a platform, then we can do the controlling immediately. No, we need to change it. Okay, so based on that, we install the MATLAB in that platform. Then by certain changes, so alhamdulillah, it can be worked. Okay, so this is how we connect to the sensors and actuators. All right, so this is how hardware set up to the controller. As you can see here, it seems like just now I'm explaining to you. So this is the image how the hardware of the robot. Okay, as you can see on the top of the robot here, at his head, okay, we put the LCD touchscreen so that we can can do all the simulation, or we can load all the algorithm inside the robot through this through this display. Okay, all right. So want to show you something here. See. Want to show some video. Can you see the video?
Not running yet.
Can you see the video?
Not running yet. Tak ada lagi. Gambar je, belum running. Okay.
Let me.
Okay, run. Yeah.
So this is the video for the balancing robot. So actually the robot is being fabricated in Hong Kong University's technologies in Hong Kong. So last time we have a problem with the the parts of the robots, okay, from the overseas coming to Malaysia. They have a very very stringent procedure on that time. So we need a lot of bureaucracy. We need to do a letter from we need to get a letter from policemen and many more. So it's very hard to complete this robot in maybe 1 year or 2 years. So that's why I'm planning to go to I have a strategies go to Hong Kong because they're very good access to the parts. So this is actually the terrain testing. So here we have a lot of bricks. Okay, so the robot still can manage to move and balance at the same time. Okay, here the uneven terrains, so the robot also can move easily. Why I put this the orange part, because a very expensive thing inside this robot, so we are afraid that it's going it's going to fall. Then you damage all the components, so that's why we put a safety net here where they got some things to stop it when it's falling down. Maximum speed of this robot is around 4 meters per second. Or yeah, it's around that. And the inclination, the slope where this robot can handle around 30 degrees. That's because of the position of the motor here. Where we put, if you want to handle more gradients, so you need to put very high, a very good motor. Okay, so next slide. All right. So that's all for the balancing robot. So now I'm going to share to you on the drones, right? So same things when we are talking about the controlling drones, you need to follow the same routes like just now we see how we control the balancing robots. Okay, you need to do a mathematical model. You need to do to get a motion equation of the drones and change it into the state space form. You need to design a controller based on that. Then finally, you need to test it. You need to create the hardware. Okay, then you need to test it. All right. The drones is actually come in package where we have we call it as a flight controllers. So inside a flight controller, when you create your own drone, for example, you assemble it without any modification on the controller. They have a lot of flight controller like Big Hawk. We also have the most cheapest is APM. APM I think is no more now. Okay, and then we have a Piccolo, very high spec. It's actually come from US. Yeah, where we can do the integration of uh, uh, hardware and the software inside that flight controllers. So when you buy it, so when you install into your UAV or drones, okay, with a certain SOP procedures, okay, you can fly. Okay, you can fly very easily. So that's why in this case, right, if you want to have more complicated controllers, okay, you need to design a very good flight controllers. Okay, you need to have your maybe a processor, a good processor, so that you can handle the change when the robot or when the drone is flying. Okay, so the drone we have classification. For example, we have fixed wings. They also call a drones. We have rotary drones. Rotary wings. We also have quad rotors, where quad rotor we have 4 motors. You also have hexa quadcopter, where we have 6 motor, for example. So all this is in category of drones, right? So actually, the best part of drone is the application of the drones. Okay, where we can do real estate photography, area surveying. We have a forest monitoring, search and rescue mission, and many more. So the advantage is the robot flying robot or drones can hover and take off vertically, right? It can be maneuver in a 3-dimensional space. It can be autonomously controlled, or it can be manually controlled. Okay, so because of that, okay, the drone is actually calm, and then it can immediately use. So we are trying to give more features to the drone, so that it will always be in safety domains. Okay, so when it flying, it have the capability to detect something, for example, the obstacle. Then it should have a capability to stop when we ask. So right now we don't have any braking system in drones because it's flying, right? So when we stop it, just release the input from your remote control. The robot is not immediately stop. It will take something. It will take some distance to stop. Okay, so that's why in this part, I would like to share to you how we going to design a controller so that it can stop when it detects something. Okay, so here is the hardware part of the drones development. So just now I mentioned about the quadrocopter. We have the APM. This is APM, APM flight controller, right? So we have a PID flight controller, where we just only tune the KI, KP, and KD inside this robot if you want to shoot with the flying condition that you have. All right. So the capability of this drone is actually we can get all the data, okay, by using a certain communication protocol. We can control it. Okay. Even if you want to apply it to the long range, for example, let's say for 4 kilometer, 5 kilometer, you need to set your frequency so that it can capable to do that. So they have many settings where we can set for the drones. All right. So even if you want to to get video. For example, I think there are no problem on the telemetries. Telemetries mean the signal to control the drones because it have a very less data, right? But when you are talking about the video transmission, for example, you want to transmit 4 kilometer video, for example, all right, so you should think about very other solutions. So like DJI, they improve their communication for video transmission. They are using light bridge. Okay, they have I think now they can handle up to 10 kilometers by using a certain configuration. So that's some of the parameters where you need to change before you decide to the application of drones. Okay, so now here is the methodologies for the TTC, means the short form for time to collision controllers here, TTC. So to apply it, so we need to have a good model of time to collision. All right. So in normally in drones there are no such thing to do or to guide the braking system for drones. But I think in car applications, okay, autonomous car application, this kind of controller is already implemented. Okay, so where the car can be autonomously brake when it detects something. So it's the same things here. So to get the time to collision model, this is how we need to follow. So first we need to do a data collection. All right. Next, we need to do a pre-processing of the data by using a certain procedure methods. By for example, we are using PSO here. Okay, to have a very good model, so that the model can be say as a good for the drones. All right. So then we do a validation, then test the model performance. So how we do the model of time collision by using a particle swarm optimization. So actually here we have the vehicle, which is a drone. Okay, we test it in a real time to collect a data. All right. So the parameters of the drones, okay, can be obtained from here. Then from that, when we do 100 times of testing, do a data collection, maybe more than that, we can download all the data flight from the flight controllers, and then we do a data processing. So here in the data processing, we are it's come together with actually with timestamp, GPS speed, and also the signal by the remote control, because we're doing it by manually here. Okay, so this is how we, after we have a data, we do a pre-processing. So we want to make sure our model is a very accurate model. So that's why we are trying to implement PSO. So this is the process how we're doing the implementing of PSO into the model for TTC, or time to collision. Right. So with a certain, here is the average weather condition during our experimental session. So from that we obtain data. Then finally from the PSO processing, okay, we get this kind of equation. This is a linear equation for the time to collision. All right. So where SW, S is for the horizontal speed, and W is actually the weight of the drones. Okay. So from that, we need to optimize the others coefficient. Okay, where we put P1 until P4. Okay, so at this point, PSO will handle the change of the weightage so that it can be tuned. So the TTC model will be accurate will be accurate with the different kind of condition. Okay, this is the main target for the optimization. So where we put as MSE as a reference to tune the P1 until P4 by using PSO to get a very accurate model of the time to collusion. So finally, we get this one, right? So after we have that, okay, we are going to implement it. So this is how we implement it into the real system. Okay, so as we can see here, this is a common. Just now I explained to you where we need to do a modeling to get the mathematical modeling or motion equation of the drones. You need to do some parameter identification. Okay, so we also have the controllers here. This is a real model where they have the existing collision avoidance system. Then we put our own here. This is a TTC controllers. Then finally we get the results based on the application, where we do a simulation by flying it through the obstacle avoided inside Simulinks. Right. So then we have the real-time implementation of the TTC algorithms. So I'm going to show you a video for the best applications. Just now, let me show you. Okay. Okay, Prof, can you see that? Can you see
Yes.
my screen, my videos?
Yes.
Okay. So here is one of the application for the drones where we think is very good if we can have the TTC algorithms. So this is the part where we are trying to have the what we call as photo or the GIS mapping for certain area uh, in forest at SIG Kedah. So we are trying to give a data to frame so that they can manage to get the what we call as data, okay, for the illegal logging. Okay, because when they give something to when they give the area to be to certain company, okay, you take a log, so they should have the data. Sometimes uh, the company will put more than the area that give by the frames. So here how we control drones autonomously, where we set the cost planning for drone. I think it's very common now. Then we set the this is the drones. Then we set the point where the drone will took a picture for each location, which set by the tree. Okay? So here the drone will be just as a vehicle to take the data, as you can see here, flying. So how LRC can be works here? Sometimes they have very highest trees. For example, we cannot see at all right now because the drone will fly autonomously. Okay, so this is why we need LRC. Okay, where the drone can avoid something. The drone can stop when it meet the obstacle, for example, so that it cannot be fly away or it cannot be crashed. Okay, so that's a certain safety where we need to make sure the drones can have to complete the task. Right. So after we obtain all the data, then we come back to the the takeoff point. Okay, so it's not a real time data collection. Okay, we can do processing immediately now. So we need to take the flight controllers from this drone and then download all the data. Okay, from we have cameras here, from the cameras. Then we do the processing. So here is the output processing. Okay, we need to have you know pictures where we can convert it. This is actually a very cheap solution compared to if you have a LiDAR. I think the disciple just now present about the LiDAR. Right? So if you have a LiDAR, you can very easily to get all real-time data. Yeah, by using plot point there, you can generate the 3D point. So this is the alternative solution. We can also create a 3D image by using the 2D image from camera. So the software called Agisoft, I think we can have that. So we can convert it into what we call as a photo image, right? So this is a 3D image. But it's not the sharp as the LiDAR. Okay, but LiDAR is very expensive. So you can get this kind of image. Here we have the contour image. Right, so let me share again the slide. Okay, so that's the some of the application. Okay, so here is the conclusion for my presentation today. So actually, to control drones, to control a balancing robot, it should follow some certain procedures where just now I discussed briefly. Okay, so the procedure can be applied to another model-based system. Let's say you want to do the modeling of robotics arm, for example, or autonomous car, for example. You can follow same routes here. Then the other control technique also can be integrated based on the requirement needs. For example, you want to change the controllers to more complicated controllers, maybe where it can achieve certain, certain requirement setting by the by your research scope. For example, you also can be done it. Okay, so by that I end my presentation. Thank you very much for your attention. I pass back to Prof. FUA'AD.
Right, Alhamdulillah. Thank you very much, Dr. Sofan, for the final presentations. So, is there any questions from the audience? If you have any to ask to our final presenter? So far, our participants, the peak participants at 25, but now it's 19 because it's already 12:15. Any questions from the audience? Okay, if there is no question, I have only one question regarding the battery life of the balancing robot and drone. Can you explain how many hours?
Okay. Okay, the drones, okay, the drones is different with a balancing robot. Balancing robot, we can stand around 3 hours. Okay, when we charge full, it can stand on 3 hours moving moving around in 3 hours. But for drones, it's only can took around 25 minutes because we have a limitation on the load applied to the drones. So normally, if the weight is more on the drone, it will consume a lot of energy. So that's why when you have a very high loads of drones compared to lightweights of drones is different. So sometimes lightweight of drone, you can have maybe 45 minutes. Okay, but if you put many things as the payload to the drones, it will reduce the flying time. Okay, so I think just now we are flying the drones by using 10 mAh batteries. Okay, so that's why it can stand about 25 minutes, Prof.
Right. So the drone is a hexacopter, am I right?
Yes, hexacopter. Yes.
Is the justification and reason why using hexacopter instead of quadcopter? Why?
Okay. Because we know that in jungle, we don't know. They have a very, the level of the wind is different, bro. So the winds when it touch the drone, it will become a load to drones. So it will reduce something. So it need a very good force to to works with the high level of wind. So that's why we decide to use a hexacopter.
So this matters about the stability matters, okay?
The stability matters and also the environment factor.
Okay, to cut off the wind gust and all the uncertainty factors.
Yeah,
Right. Thank you very
exactly,
much,
exactly.
Dr. Sofan, Wahyudi. So with this, we ended our
Sorry, Prof. Sorry, I have another question. Sorry.
right,
Okay. When you talk, Dr. Sofan, when you talk about collision avoidance, right?
Yeah,
So, what kind of sensor that you use on board the drone for detecting?
Okay, we have the ultrasonic sensor to detect the obstacle, and then it will give the input to the algorithm to check the model of TTC, okay, to assist the drones to stop at the certain specific range.
I mean, on board. I mean, when you do the flight test, right? So that time, so you put the ultrasonic sensor on board, is it?
Okay, yeah.
Okay, how many sensor you put? I mean, only one set sensor, or you put the
Yeah,
sensor
we
all
have
around
to,
the drone?
we have because the drone have forward and back, they have a direction on that, so we put two ultrasonic sensor, front and back. So when the drone moving forward, because it had less, so sometimes it will use a front ultrasonic sensor, and sometimes use a back ultrasonic sensor. So from that we get the data of the obstacles in front of the drones.
Okay, how far is the measure?
It's around 6 meter.
6 meter,
Yeah.
right? Okay, all right. Thanks.
Okay, thank you.
Dr. Shabriza from UNIMED, you raise your hand. Okay.
Assalamualaikum, Prof.
Yeah.
Minta maaf, a very quick question. Very interesting application on the drone for mapping.
Yeah.
I'm just wondering, can you provide information on the accuracy of the mapping? For example, how accurate on the mapping on the after you have developed the 3D mapping
It's around 5
compared to
meter.
the
It's around 5 meters.
real.
It's quite big. It's around 5 meters because we only use because the GPS have the errors sometimes because the cloud it cannot get a very accurate position. So that's why normally we get around 5 meters.
So for this mapping, the accuracy, does it change depend on the flight? Let's say you take this route, or let's say cloudy days, let's say about to rain, let's say shiny days. How about the accuracy changes? Thank
Okay,
you.
so that come for the when we do data processing. Okay, when we do data processing, we try to align it so that it will give a very minimum errors for the reference position of the real position in the current settings. Okay, let's say we are doing by Google Map, for example. In that location, we set it. Okay, so when the drone flying, so we'll get the different errors. So when we come to the data processing by using Edison, we can tune that so that it will give you a very minimum errors by the position. Okay, so I think it doesn't matter if when you are flying with a cloud, because when you are flying with cloud, it will affect to the drones itself because sometimes it don't know the location. So normally we will set some rules there. Okay, So they will get the next position by given reference in the mission planner, which is upload into the flight controller in the drones.
Okay, thank you very much.
Okay.
Hafiza, I think I have one last question. I think you didn't touch about the noise generated from the six propeller. So when you run the drone, of course, we have a very noisy
Yeah.
from the propeller of the drone. Is there any approach to cancel out the noise?
Okay, Prof. There are no problem on the noise, Prof. The most problem for drone is actually the vibration.
Vibration.
Yes, yeah, vibration, because the vibration will affect to the structure of the drones. So when the vibration affect the structure of the drone, it will transmit to the flight controllers that it will very dangerous on that time. Okay, so if very high vibration, so the controller may fail because of the vibration. So that's why sometimes to avoid that, they will put like a rubber, like a damper to make sure the flight controllers is not affected. So the noise, there are no problem at all, bro. So the most important where they're trying to avoid is they need to do a cancellation of the vibration. Okay, because when we flying, they have a lot of vibration on the structure of the drone itself.
Okay, thank you very much, Dr. Sofan. I
Okay,
guess
thank you, bro.
we finally ended our sessions today. Very long sessions. It's 19 past 12. Well, thank you very much for the speakers. And thank you very much to the all audience. So we'll see again in the next International CMED webinar somewhere in September, inshallah, end of September. So by that, thank you very much and see you all later on. Thank you. Assalamualaikum.
Waalaikumsalam.